In the last video, we discussed the mass continuity equation, which is written here. And in this video, we will be discussing the moisture continuity equation. For the mass continuity equation, we wanted to know how rho changes in time. But for the moisture continuity equation, we want to know how Q changes in time. Now, what is Q? Q is defined here. It's the mass of some sort of moisture-related quantity divided by m, the total mass. So we have some air here, and we want to know how much water vapor gas is in the air, because we don't have all of the air being taken up by dry air. We have some areas where it's white, which is dry air, and then we have the little moisture particles that are showing up. And so for water vapor, we call that QV. And as you see in this equation down here, we have the QJ, where J can be, V, it could be L, liquid water, C for cloud, R for rainwater, etc. And, if we're interested in QL, that would be how much liquid water is in there, which is different than water vapor, because water vapor is a gas and liquid is not. So to get started, we know that the rate of change of water vapor fraction is equal to the moisture conversions into a volume plus any moisture sources or sink, not necessarily water vapor, sorry. So it's moisture sources or sinks. And so if you remember, negative divergence is called convergence. And so what we've written here is, and that's per unit time. So what we've written here is that the partial derivative partial time of the density times Q, because Q is a fraction, it's between 0 and 1. If it's 1, it's 100% of water vapor, for example. So this is really saying what percentage of the density, where this is dry air, it's saying what percentage of that is, this is actually density of the entire air. Sorry, the density of the entire air, including those moisture in it, it's saying what percentage of that are we taking. And that is equal to the convergence, negative divergence, of that same quantity, moisture convergence, which is this entire term, because we inside of the divergence, instead of the regular divergence of velocity, it's divergence of the density times the velocity, or the density fraction times the velocity, plus the source sink term, where S is for source and for sink. One of these, for example, SJ could be condensation. There's other ones, sublimation, turbulence, diffusion. Another one you probably know is evaporation. This is basically saying that for condensation, that's when we have a bunch of moisture, water vapor gas, and eventually they combine together and they form water droplets. That would be QV turning into QL, or that basically means the same thing. That what that means is that QV is going down while QL is going up. So that means this convergence of air and moisture is entering the region. That's what this term is saying. But this is something that's happening within the region, basically. And evaporation will be the opposite, where we have QV is going up and QL is going down. And that usually happens near the surface. But can really happen anywhere throughout the atmosphere as well. So now we have a set of equations. We have the one we just discussed here, and we have the mass continuity equation. And what we can do is we can take this one, subtracting Q times this equation. So this entire equation minus Q times this entire equation. And first we start with the left-hand side. So we have partial rho Q partial T minus Q rho partial t. And we can use the product rule here, so we get rho partial q partial t plus q partial rho partial t. And this term and this term are opposite, so they go away. They're the same, and this one is negative. And we're left with this term. And now looking at the right-hand side, this term goes for this one goes for this one, so we end up having it here, and then it's minus this one, so it's plus q times this same term. And then Sj as well, I forgot to mention when it was going here, Sj's here. And we discussed in a previous video about like using a vector calculus identity. Here's it might be the same one or a similar one to get this term here. And if you notice, this term and this term are opposite, so you can cancel them, and you're left with this and this, which is here. So now we have that this is equal to this. We can divide density out now. So density is literally gone from this equation, and we're left with partial q partial t minus the advection of q, the mixing ratio q. And we can actually write this equation, because if you remember, the total derivative is the partial derivative plus, which we added to this side, plus the advection of some of that variable. So this equation is really saying, oh yeah, and we also have this Sj, and we divided the rho. This equation is really saying that total derivative of q for some type of mixing ratio is simply equal to the source term. So the change of q in a region is just how much is getting advected into that region plus the source term divided by that density. And we already discussed what some of those source terms can be. We talked about in the case of condensation, how that's, and evaporation, is how that's dealing with QV. So where J is equal to V and J is equal to L. And there are some other ones that we can include. And we can, this equation holds true for each of them individually. And we can also later, we can see, we can add different ones together. Like there's another one, ice. You can add C and I to get the anvil, the things that are going on to represent the anvil of a cloud, all the moisture processes going there, totals. But the nice thing about this equation again is it works individually on its own for just water vapor on its own. And so basically what we would need to do is, if we're dealing with condensation, we have some QV is turning into QL. What we need to do is we need to solve dQV dt. So I'll write that so it doesn't disappear. dQV dt is equal to the advection of QV plus some source term. And then we also need to calculate the change over time of QL for liquid water, which is equal to negative advection of QL plus QL over rho. And this term here, this will be SL. This will be SL. This term, SV and SL. And so this term SV is actually dependent on QL. And this term SL is actually dependent on QV. So you need to solve both equations to update every time, and we need to find equations that represent the fundamental physics, microphysics, convection processes that are give us an equation for these. But at this point we don't know them, but if we knew this equation, it would be dependent on QL, and we would have to solve that at each time. So this can get extremely complicated because we need to solve equations for every single one of these, so we can separate out the different types of moisture, and so we can take into account all of these types of moisture processes, which can eventually go back in and affect the temperature and thermodynamics of the cloud, because a lot of these terms are involved in the heating term of the equation of thermodynamics equation. The sun can come in and it can hit some of these particles, and the heating can be reduced. So there's a sink to the heating that's coming in from the sun. There could also be things that increase the heating. There could be the release of latent heat. So latent heat release from these moisture doing different things in the atmosphere can mess with that equation. And if temperature is changing, then pressure and density are changing by the equation of state. And so things can deviate very quickly from the equation of momentum. So the momentum equation is really a full equation that works perfectly, but there's other equations that are coupled to it, like the thermodynamics equation, which is very dependent on what is going on here. And so that is oftentimes a lot of these processes, like condensation and things that go in these, are not known with a real full equation like we have for the momentum equation, and we're using what's called parameterizations, which are basically like laboratory experiments turned into basic linear relationships and things like that go into calculating or estimating these terms based on non-equation, non-direct sort of calculation method. So in the future, I hope to talk more about some of these processes as I learn. So please, if you like the channel, please like and subscribe, and keep staying tuned for more videos. Thank you.